I'd love to say that after you just had a 10-minute break, now I have a quite smooth and relaxing talk for you, but I'm sorry, I'll have some hell of a talk for you for the next 45 minutes. So it's about 80 slides with tons of code on them. So just trying to warn you a little bit. And I'm going to crush some myth about asset transactions and some romantic views that some people have about NoSQL databases and stuff like that. So don't say I didn't warn you. But anyway, we'll see how it works out. So I try to be as nice as possible while doing all that. My name is Uwe Friedrichsen, and we should skip that part because we should focus on the rest of it. So working for concentric, blah, 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 and so on, whatever. Let's talk about asset versus base. Who does not know what asset transactions are? Ignore this guy. Okay, so we all know asset transactions. We are very well used to those things, and asset transactions are great. Really, they are. So no joking. Asset transactions are a great thing, especially in a point of view from a programmer, because asset transactions means they're easy. They have a great programming model. I mean, this atomicity means it all works, what we're doing within a transaction, or nothing works, which is cool somehow. So we start a transaction, and then we do some changes that are related to each other in some way, and then do a commit, and either all in between works or nothing works. We don't have to care about situations where parts of it works and the rest fails. Cool stuff. And also that isolation thing is really cool, because from the outside view, you either see the state you had before starting the transaction or the stuff which you have after the transaction commits. Great. Saves us from a lot of trouble, cool thing, makes life easy for us as programmers. So why base transactions then? Base transactions came into play where asset transactions started to fail. So there's situations around, especially when you go to scale up very much, where base transactions have asset transactions have a problem, because asset transactions don't scale very well across several nodes. So on one node, they are great, but across several nodes, the cap theorem comes into the way. So you heard about that probably this morning, the cap theorem already in the talk this morning, where you have this consistency, availability, partition tolerance, and as long as you're on one node, it's great because the cap theorem says you can't maximize all three of those properties at once. You can only maximize two of them. So I don't say you can't have all three of them, so pick two of them, because that's wrong, that's an oversimplification. But as long as you're on a single node machine or high availability cluster or something like that, which gives you the illusion of a single node machine, for instance, Oracle Rack cluster, whatever you have there, you can maximize for availability and for consistency, which is okay. But as soon as you start to distribute across several nodes, partition tolerance, which means that you must be able to deal with partitioning of your cluster, so either by a network problem or by some machines going down in between and coming up later and so on, that you have to be able to cope with that, to deal with that. So partition tolerance isn't an option anymore in distributed systems. And then you can't get full availability and full consistency. So you have somehow to balance between those things. And that's where those base transactions came into play. It's a word play, so asset versus base, the English two terms. So the first three letters you can basically ignore here. The E is the interesting one, eventually consistent. And that's, again, the slide that you probably might have seen this morning also, the original one from Brewer, which he used in a talk in 2000, where he introduced the cap theorem and also base transactions. And if you see through that stuff, you see here best effort, it's simpler, it's availability first, which it's faster, easier evolution, sounds very nice. But there's this one thing up here, weak consistency. And this has some consequences. Actually, this has a lot of consequences for us as developers. So in conceptual terms, what are the consequences? It means we do not have any asset properties anymore across entities. So if you have two different entities that you're going to update, you have to update them individually. No asset properties across that. And you also don't have any asset properties across nodes. So if you're dealing with replica sets, you very often deal with replication as a means of failover guarantees and some other things, also redundancy pattern, which is used then. So, then you also have no guarantee that the same entity on different nodes has the same value anymore. So it's also no asset properties here. One asset property is left over, so one entity on one node is updated in an atomic fashion, usually by all databases. There are some NoSQL databases around which have more properties, which give you more guarantees, which says, I give you asset properties or asset guarantees on a complete node, but you have to really look carefully into the documentation, what the database that you're going to use is going to tell you, so which guarantees it gives you. The general case is this. And what does it mean for us as developers? I said this has some consequences, but which consequences does it have? So let's start with a very simple example. So the most simplistic one I was able to come up to show you or to give you an idea what it means to work with those base transactions. It's a very simple library example. So we have some customers, some books. Customers can loan books, books can be loaned. We have 4 actions here. So you can loan a book, you can return a book, and you can ask which books are loaned by a customer, and you can ask if a book is loaned. That's it. So two mutating actions, 2 read-only actions. And to show you the problems that are going to arise with base transactions, I will start to implement that in a very simple fashion, in a traditional way first, so with relational databases, asset properties, JPA, and then we're going to transform that in a naive way to a NoSQL database, and then we will hit all those challenges which are around and trying to develop that and figure out techniques how to deal with those. So let's start with the first iteration, with a simple one. So that's quite familiar probably for most of you. So we start with our domain class. We have those annotations. It's an entity. We have some ID, some generated value for the ID. And maybe the only interesting thing is this one-to-many relation, which is used for filling this data structure down here. And it uses an attribute from a related class, which you find here, down here, to set up this mapping. Yeah, that's no magic. We all know that probably. So most of us probably know that. And if you look down to the database model, it's also quite straightforward, 2 tables with a few attributes and a foreign key relation in between for keeping up the referential integrity. Yeah. And going further for the code, here you have the loan action, and here's what we talked about. We begin the transaction, we read the entities from the database, and then we do the modifications, we persist it, and we do a commit, and that's basically it, all the magic. And all the rest is handled by the JPA in the database itself. And either all of this works or nothing works. Yeah. Same stuff for return, just a little bit different modifications in here. Then if we look for a loaned book, we just create a query in some kind of an SQL dialect here, where we say, yeah, we want to find the book with the right ID here, and we get the result, and then we can just operate on the result we've got. Yeah, so is the customer set or not? Yeah, true or false, that's it. Again, no magic. And the books loaned are also quite similar to that. except that this is a data structure, and if we do that last thing down here, customer get loaned books, which gives you the list of loaned books actually, it triggers implicitly, that's what your JPA framework is doing for you, your Hibernate or whatever you're using, triggers implicitly additional queries. So to the database. So first up here you just read from the customer table, and down here you read from the book table actually to figure out, so with your foreign key relation to figure out what's to be in here. This becomes important later on when we see how most NoSQL databases handle this, because a lot of comfort is going away in here. And for doing this where part, quite often a secondary index is used for getting efficient queries done, so that you're not having to scan the whole book table to figure out which books match, but just to pick the few ones where the custom ID is set. But that's basically it. That's the whole magic of the classical asset approach with JPA and stuff. So to wrap up with that part, any mutating action usually has a schema: begin the transaction, do the required changes, and then commit. And the non-mutating read-only actions, it's creating the query, execute that one, and then navigate through the result set, while this navigation fires implicitly additional queries. It's a nice thing. We are all used to that. We like it, or actually we're a little bit bored of it meanwhile, and so maybe some of us hate it meanwhile, and we want to do some new cool shit, of course. So, and this NoSQL stuff is really cool, so let's do that one. We don't know exactly how we get our manager convinced from that, but we finally get the chance to program something into that. And we are going to program this stuff in that. So let's start up. How are we going to do that? I mean, there's all this cool stuff and around, and what I've seen way too often is that what I called the naive approach. And I'll show you what I mean with that. The naive approach is we take what we know, the asset approach, and then we look at this and say, what do we have in our new API available? So how can we bring that into the new world? This is what we know. And we see these transactions aren't there, so these begin transaction commit, we don't have anything in our API. So let's skip that and hope that it works. It will work. I mean, the vendor says it's blazingly fast, it's reliable, it's safe, it will work probably. I mean, hope's our friend. And for the other stuff, for non-mutating, yeah, this querying and executing, that's working. This navigation, we don't find anything for that. So let's skip that for the moment and handle this in a different way. And this leads then to something, to a new approach here, so to a new model. Let's start with the database schema first. So we have this old schema here. And I mean, we want to do new cool stuff. So let's no longer go with some tables. Let's go with some JSON stuff. So some JSON documents. These are much cooler than databases. And books here, yeah, we also map that to another JSON structure. Straightforward, no magic in between. And so don't get me wrong. I love that JSON stuff. I love new NoSQL databases, anything like that. It's just with all the happiness we have, there are challenges in here. And that's it's my point today. For this entity class, yeah, we know that all these annotations are gone. So let's throw it out, actually. We have to take care about that ID generation on our own, but UUID is our friend, so it's not big magic for that. And we end up with that, which is quite exactly the mapping of our database model. So our domain class and our entities are the same meanwhile. Same thing for the book side. So we have to get rid of all that, and we just stay here with the ID. Right. Okay. Now how's the code looking? If I want to read a book, loan a book, so I start reading the book first and then doing the modification, which is setting the custom ID and then writing it back. By the way, this is quite a quite a good pattern which you should use most of the time in NoSQL databases, read, update, write pattern. That's quite familiar there. This gives you less trouble because you always change the whole entity and not parts of it, and not trying to do magic between entities. So for instance, Mongo gives you this nice update queries and stuff like that, but there are risks in it. Most of the time they work. Problem is that it's most of the time. This pattern is safer, but it's more work on the other hand. So some APIs, for instance, React gives you a complete API with that, where you just put your update as a callback function in, and then it all works out of the box more or less. Same thing down here, and is books loaned? Yeah, no magic. I don't have to go through every single line for that. And if we read a book, so we do the real database call. I just did an abstract one here because depends on the database you're using. If you're using Cassandra, it looks a little bit different as if you're using Mongo, or if you're using React or Redis or whatever. But the base idea is always the same. And you have to convert that from the domain model to the entity model. I mean, your mapper is gone, so you have to do it by hand again, which is also no big magic. So we're using Jettison here. Use your own magic here, whatever you want to do. Yeah. Right. Other direction also. So if you want to write, you also have to map from the domain object back to the entity model. By the way, there are also databases which gives you callbacks for that, so that you just say here is from domain to domain, and then it all works. So just some callbacks you have to put in. The only thing that might be a little bit interesting, because it comes back to us later, is this books loaned. What we have to do here is actually we have to read somehow all the books and scan the stuff if our custom ID is in. I mean, all these other nice things, secondary indices are gone, and all these other nice things like navigation and all that stuff is gone somehow for the moment. So, but our test data is quite small, and all is still blazingly fast. Okay, yeah, okay, the iterator here, it's just doing a little bit of mapping in between while doing the iteration, but we can skip that part. So we're quite happy with that. We released that. I mean, we did our first program with NoSQL databases. It's cool. And it's really cool anyway, but there are these challenges, and now they start up. I mean, we put that into production on our system, our test system. It all went great. On our development computer, it went great for sure. I mean, otherwise we wouldn't have released that stuff, and cool. And then in production, some strange things start to happen. The first thing is, and you sometimes get some strange results back. So for instance, if you take those two commands saying customer number 2312 wants to loan book number 4711, and afterwards you query if this book is loaned, you usually expect to get back a yes, true, yes, it's loaned. The problem is that this action is behaving like an average consultant. It tells you, well, it depends. And that's bad somehow. And I tell you why it behaves like a consultant. You have two alternatives right here. You usually have a replica set. So for you don't use expensive SANs to store your data with automatic backup and all that stuff. You just say, you store it on 3 nodes, and on cheap machines, on standard, out-of-the-box, off-the-shelf hardware, and that's it basically. And so 3 replicas. And for read speed up, you say read from any node. And in the beginning, you also say write to any node. So you don't care where you write to, where you read to. You want to scale, actually. And one situation is your loan action goes to, hits that node, then the application takes place, and afterwards there is loaned, which hits that node. I mean, there's probably a load balancer in between or some routing strategy, which we don't influence actually, comes back to you and says, yeah, it's loaned. Everything's fine. Well, there's another alternative. I mean, it's clear. You write to that one, and before the replication takes place, you ask another node, is that book loaned? And it gives you the old state, which probably is, no, it is not, which isn't so nice. So we don't like that. What are strategies to handle that? First one is quite well known, this pattern, as read your own writes. Read your own writes is a configuration option that you'll have on many of those databases. Read your own writes means no matter, so you decide for one of the nodes where you write to, and if you write to a node, you also read from that node and not from a different node, which is a fine solution, which might be sufficient. If it's sufficient for you, use it. It doesn't work all the time, unfortunately. For instance, imagine the following scenario. You have a web page which goes, JavaScript application, which talks to a set of REST servers, which in turn talk to your database backend, which is quite a familiar scenario today with JavaScript applications on your browser. So what's going to happen? Your JavaScript application sends a request, it hits the load balancer. I mean, your REST servers are stateless, they're scalable and stateless for sure. It's a load balancer, it picks one of your REST servers, and this REST server reads its own writes, which is nice. You do the first action here, and then the second request goes, hits the load balancer, it sends a request to another REST server, which reads its own writes from a different node from the replica set, and all your strategy is toast. So it doesn't work always. So think carefully if it works. If it's sufficient, use it. Otherwise, it's a little bit easier sometimes with the read from master, which only works, of course, with master-slave scenarios. Not all databases are set up in a master-slave scenario. Some of them are masterless, and then, of course, you can't use a master-slave scenario. Read from master is basically the same pattern, but you set up your replica set with one dedicated master node and some slave nodes. You usually use the slave nodes also for read actions, so you always write to the master only, so to have one single source of truth. But you use the slaves usually for read speed up. So it's a typical scenario when you say you have few writes, but you have many reads, then you use that strategy for scaling up usually. So scaling your transaction numbers, not your data necessarily. And you also decide then, also an option, for instance, for Mongo, it's an option that you also can say, read from master. So you don't allow any reads from the slaves, which is also okay, which might be the solution for your problem. Only problem now here is your scaling is gone. If you can deal with that, so these slaves are only for data backup left over. So if this machine crashes, those can take over. So it's only failover. It's no scaling anymore. If that's sufficient for you, you can use it. Okay. What else do we have? Any programmatic approaches? The common approach here is, or the more general approach, which is not offered by all databases, is a quorum-based approach. That's how you can fine-tune what exactly you want to have, which characteristics you want to have. Quorum is building consensus or getting a consensus in a distributed system. It's a general pattern there. And in this special situation, you have three numbers to deal with. It's the n. N is the number of nodes which are involved in making the decisions. It's the w. W is the number of writes you want to have confirmed that they succeeded before you consider a write action to be successful. And R is the equivalent on the read side. R is the number of reads which give you the same result before you accept this read as successful. That's basically the three things. So quorum-based approach is quite a big deal actually, so we could talk about half an hour at least about that, but I try to keep it short, therefore I strip that down a little bit. If you would like to have ACID properties, you would set n equals r equals w. So all nodes have to be written before you confirm the write, and all reads have to give you the same result before you accept any read action. Full consistency, asset properties. If you're a little bit naive, you set o's of n, let's say 3 nodes, okay, and you set read to 1 and write to 1. That's not even eventual consistency, that's accidental consistency, because everything can happen to you. So if you're a gambler, that's the right setting for you. And the better one usually is, this is what you see up here, that's the 2 constraints you have to fulfill to get eventual consistency, which means you are guaranteed to get consistency, but you do not get it necessarily immediately. You will get it eventually. So these 2 formulas, I mean, you can think about it for a while after the talk. Let's assume n to be 3, and then is w must be at least 2, so 2 confirmed writes before you accept the write action to be successful, and r plus w must be larger than n, so r must be also at least 2, so you must get 2 reads with the same result before you accept the read. And if you think about that for a while and it's clear, yeah, this means eventual consistency. That's okay. Some of the databases offer support either in their configuration or even in their APIs for doing that. So some do that just as a general parameter, and some others you can configure that as on a call-by-call basis. And if you have that, I mean, it's not a big deal in here, so your read actions only take these additional parameters. So for instance, if you look at the React API, you can also put that with every read and write action, you can add the quorum you want to have. I always mention the React API because it's a quite complete API in terms of what can happen to you, and therefore I like it. If you really want to know what troubles you can have and which ways are available to deal with that, React API is a quite nice place to learn that. You see the quote this morning, it took a year to learn React. Yeah, that's true, but it's a good way, it's a good place to learn. Okay, but we fixed that. We found our strategy. Great, we've done. Production is cool. But then something else happens, which is a little bit strange then, because we get some strange errors in between where we don't expect them. And we have no clue. I mean, we execute that thing here, which is quite straightforward. And I mean, it isn't that hard. It should return a true or false and nothing else. I mean, there's no magic in between and nothing. And it sends us a strange exception, a JSON exception, actually. You say, what the heck's going on there? And so we go into that code and we see, yeah, this is book loaned. This boils down to this, yeah, here's the function, and it reads a book. And read book reads from the database, and it calls this to book. And this to book is doing the conversion. I mean, I put in here a book JSON, and it's doing this stuff here. I mean, it's everything fine. Where the fuck is this JSON exception coming from? Problem is, what's coming in here isn't a book JSON. It's something that looks like that, which is a little bit odd. And what you've got here is siblings. So you had this partitioning, this split brain situation, where you got a partition in your cluster, and when it comes back, your cluster can't decide which of the 2 changes which happened in between were the right one. So you had 2 independent changes to parts of your cluster, and you're sitting there and don't know is the old state or the new state. So is it actually loaned or isn't it loaned, the book? I don't know. The database can't decide for you, and therefore it gives you back this cluster. The sibling. And says, it's your turn. Decide. What can we do about that? First strategy is our standard strategy that we love very much that we are very much used to. It's leave it to the caller. So wrap it into another exception and throw it to stack up. If it's a runtime exception, let it go through. And if it's a normal exception, wrap it into a runtime exception and throw it. Great. We're done. No longer our responsibility. Which might be okay in to some extent, because maybe at the place where we get this strange exception, we cannot decide. Problem is that usually this tends to go up all the stack, and finally it will be left to the user of the system to decide which is the right thing. But it's not the best idea to leave all these decisions, which have their root cause in a technical error, to a user. They don't like that. They say, get yourself a fucking relational database and I don't have that shit anymore. But you don't want, so you have to handle that yourself. So you come up with the idea to build a resolver. So you have to have some criteria in your data to decide which is the right one, the first or the second sibling here, or if you have more than this, which is the one to pick. Actually, the data we had in place wasn't sufficient, so we have to add some data. In some places, you might have a business criteria, so business-related criteria, a functional criteria to decide that. In other places, you have to add artificial criteria, so you can use vector clocks, which do not solve this problem completely, or do some other tricks. Here we are just using the approach that Cassandra uses, so we use a timestamp. Timestamps are risky too, because time in a distributed system is a hard thing to get this clock synchronized, and even if you get the clock synchronized, it's still a hard thing. So absolute ordering in distributed systems, there are thousands of pages been written about that stuff. All right, so how does it look if we build a resolver? So we try to go with that timestamp. First, we have to add a timestamp to our data. I mean, if we read it, now we have the data. Of course, we don't want to have that in our domain classes, because here we don't want to see any siblings anymore. It's in this conversion step in between. And if we write the data, we add the timestamp when we wrote the data. And if we read it and convert the stuff, we have this additional thing in here, so we have this resolve book in between. And the resolver isn't big magic, actually. So what we're doing here is we look, is there a sibling in place? No, then it's probably a normal JSON, a normal book JSON, so we just return that, and otherwise we just scan through the data and look for the newest one and return that one. And the conversion function works again. The nasty exception is gone. Valid strategy, definitely. And you might need to build that to get hold of your siblings. There's one more strategy which is in place, which is really cool actually, but unfortunately doesn't work for everything. That's what's called conflict-free replicated data types, CRDTs. It's a quite cool paper, so if you if you just Google for that term, you will get the paper. I don't know exactly who wrote it, but we're quite smart guys, and it's quite readable. So it's still a scientific paper, but you can read it without falling asleep immediately. So it's worth reading it. And the idea here is it has to do something with math. So you work with stuff like Bloom lattices and semi-monotonic what's it called? I missed the term. Semi-monotonic functions and stuff like that. And the core idea is whenever you update your data, you only change it in one direction. For instance, if you have a counter, you do not count up and down. You split it in two counter, in the number of increases and the number of decreases. And if you always do this, you can automatically technically merge that stuff. Can do the same thing with arrays, with with lists, with sets, with some other data structures, with more complex data structures. You still have a little bit of garbage collection to do somewhere in time, especially for data structures, so get rid of stuff that is obsolete, but this can be solved. So this isn't the big deal to get that done, and it's not very risky to get that done. But it's unfortunately it's out of scope here. So if you're interested in that stuff, if you're really dealing with NoSQL database and you have those problems, read this paper. It's worth it. Just scan for the term. Now we have solved our problems and we are quite happy. We have these inconsistencies, these siblings, so what else could happen? Unfortunately, these users are still not happy, even though we solved all our technical problems, because they say, you know, I've got this odd problem that when I try to loan a book, it takes very long and sometimes it doesn't work at all. And you say, why the heck? Problem is, when you boil it down to this simple function here, which is going to take place. So because you have a limitation, if the customer already loaned a specific amount of books, you won't let him loan another book. And this takes somehow internally. And of course, if you look into the code, you see here is this read all books, which takes so long. Because at the moment, we go through all the database, read every single book and look for the result, which isn't nice, actually. It's like a full table scan on a relational database, what we're doing. And even worse, if our data is so big that it's sharded across several nodes, some of the nodes can be down and we don't get the complete result or no result at all, depending on the settings of your database. What can you do about that? The first one is straightforward. Secondary indices. Some NoSQL databases offer support for secondary indices, which is nice, which can solve your problem. So you add that secondary index and you read using that index and you get your speed up. It's okay in many places. But it still has some trade-offs. So the first is the most important one. Secondary indices are only reliable if you are able, as a database, so if the database vendor puts the secondary index information for the entities on the same node and guarantees asset properties for the whole node, not only for one entity, because every entry in a secondary index is an entity on its own. And if you update those in a non-asset fashion, your index gets out of sync, which is a problem, actually. And the last one, so let's leave out the second one, and you still don't have solved the problem that if your data is distributed, some nodes can be down. And then we say, yeah, secondary indices are nice, but are they sufficient? I don't think so. What can we do about that? And you step back a little bit further and you ask yourself then, why the heck I am going to use these books and read through all the books if I want to get a property which belongs on a logical point of, from a logical point of view to a customer? I mean, we're used to that so much from our relational databases, how we map these one-to-n relations, that we don't think about that anymore. But if we step back, why don't we just read this one customer info and we have it? So why are we going to read through all the books in the library? I don't want to do that. And that's actually what's taking place in most NoSQL databases that do denormalization. So if we have two related entities, we store the association information on both sides, usually. Which means here we have to extend our data model with information from the other side, also on the here with the book entity. We have to enrich our domain classes on, now it looks more similar again, so it looks quite, we know that. It looks almost like our JPA stuff. And sorry, let's stay here. That was too fast. Here we were. Sorry, here. But it isn't JPA, so we can just navigate one step. We can't navigate through all of that. And same thing here, we don't have that ID anymore. We have a customer object again, actually a reference object here, which I call that. And then, we have to update these mutating actions. So we are no longer only mutating or changing the book entry, but also, of course, then the customer entry in this cases when we are doing updates here, so adding the code for that. And our mapping is also updated in between. Also some more mapping, which is updated. I mean, doesn't take so long to do that stuff. So not so important. But here it becomes a little bit more interesting. So what do we get from that? If we go to that books loaned, which before cycles through all the books, it's just one call to the customer and we have the information in place. We just go down out to one node, do one read, and we have it. Real good speed up. And that's actually, and yeah, this here no longer comparing to some arbitrary ID, but to is not null, which is a little bit more expressive, but okay, we take that along the way. Let's wrap that up. It gives you huge speed ups, and it's a quite common technique, and it's so common that here we have an example where we have two lead entities, so independent entities. But if we have aggregations or compositions, like we have a customer who has addresses, who has other contact information, who has some subscriptions, and blah, 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 blah. So one lead entity and a lot of dependent entities below that. Usually they're brought together into one cause entity if you do database modeling for NoSQL database. So you have a very different approach to do data modeling for NoSQL databases than you have for relational databases where you all normalize that stuff. Because of these missing asset properties, you denormalize all the stuff. You bring it back together. Which is great on the one hand, easy access and huge speed ups and all reliable. Problem is that you run into inconsistencies again. Now across entities, which is bad. So it starts from the beginning. I won't go through that anymore in detail. Just say, then you have to think about some strategies which are similar to the one you've seen, so resolvers, but now across entities, on-the-fly resolvers, which has their pros and their cons. Then you have strategies like read repair, which are not only resolving on the fly in your memory, but also writing that back to disk, which has some trade-offs because maybe you just have a timing issue and therefore you have this inconsistency in there. So you update an entity which will be updated afterwards and which can be strange again. So all these things have these pros and cons, and you go for more advanced stuff like consistency crawlers, which will try to prevent that stuff or update automatically in the background before it gives you a problem. Or you run into things like journals because you must guarantee eventual consistency, and if your node is down, you must keep that, or in other strategies like hinted endoffs and so on. So we could go on for hours here. There's a lot of stuff which is going on here. Yeah. So let's wrap up. I didn't want to scare you about base transactions. Honestly, I didn't want to, and I hope I didn't. It's cool, it's great. But it's got some challenges. And if you look at the challenges, you see the only reason that I see for asset transactions, by the way. There's only one reason in the world that you really need asset transaction, or that you might need asset transaction. That's the programming model. So all the people are around just for crashing this myth and tell you, we need asset transactions and these are functional requirements, this is business requirements. I said it's bullshit. Well, say, think about this banking example, for instance, with these money transfer. I mean, you withdraw some money here and you deposit it over here for your transfer, and you must do that transactional. It's a business requirement. And I say it's bullshit. I tell you how it looks in the real world. If I transfer money to any account of yours, what is going to happen? The money is gone from my account. Whoop, vanished. Gone, away. On your account, nothing. 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 Depending on how brave my bank and your bank is, it takes a day, usually 2, 3, 4, 5 days, and then eventually the money pops up at your account. Eventually consistent. The real world is eventually consistent or inconsistent at all. There is no thing like asset properties in the real world. It can't be a business requirement. It isn't. It simply isn't. So It's nice, it's convenient, but it's not a must if you think about it really carefully. Asset properties are nice from a business point of view, but they're not a must. The only must I see is this stuff, because it can be too hard for the developers to handle base transactions. It can be. Still, it's cool shit. Of course, the marketing guys are around for the NoSQL databases. They know about these problems. Say, oh, that's no problem. We built that one database. It's scaling like hell. It's completely distributed. And it's blazingly fast, and it's completely consistent. We've got asset transaction for everything. We got across the cap theorem, which is bullshit. Sorry. So they're just lying. You can't fool the laws of distribution. They are there. They can't be beaten. It's proven. It's scientific proven. And if a marketing guy tells you, we got along across things that are proven, rock solid, he's just lying. It's not there. It's out there. So these inconsistencies will happen. Use NoSQL databases. Have fun with it. I have tons of fun with it, actually. I love them. But you've got a price to pay. And that's the only thing I wanted to bring across. Be aware of the price you have to pay. It's not for free. But then have fun with them, and lots of fun. Thank you.